Suppose in a quiz has 10 questions, and then this is a multiple choice questions, have 4 answers per question. Suppose you know nothing about that, you just a random guess. So X is the number of answers that students guess is correct. Okay. So multiple choice, there's only one correct answer per question. What's the probability? It's just a one question you got it correct. Yeah, 25%, right? So here, so first number of, so X follow binomial distribution, right? N, what is N, what is P? Two parameters define the binomial. What is N here? 10, the 10 question, I tried 10 times, 10 trials. The probability of success of each trial is 0.25, right? So we defined the binomial distribution, and then we know the expected value. What's the expected value for X? That's NP, right? So that's 10 multiplied. So on average, if you try again and again, on average, you got 2.5. So now you can answer the question, X follow binomial distribution. Normally, we type just X follow. So this tilde means follow. Binomial, we use bin and 2 variables, 2 parameters to define it. So we know X follow binomial distribution. So this is how you answer this question. So what's the mean and standard deviation? So this time, mean. So this is the mean. And then standard deviation, we use the sigma X. Sigma is the square root. Type here. Equal to square root of N is 10 multiply 0.25 multiply P and 1 minus P. Okay. What happened? Oh, need a multiply. Okay. So you find out the mean and the sigma. Okay. So next question. What's the probability a student gets right on 5 questions? So how we can change this, translate this into the language of probability? What's the probability gets right on 5 questions? So that means your random variable X equal to 5, right? So we like to know the probability X equal to 5. So X equal to 5, we know we have the formula here. So this is the formula, right? Type here. So all I do is based on the formula, and then we translate it into the Excel functions. Excel has already have built-in binomial distribution function, so you don't have to use the typing the all these formulas. We just use binomial distribution function. See, binomial distribution, and then number of S. That means number of success. That's in this case, I success 5. Out of how many trials? 10 trials. Probability of success, 0.25. Cumulative, if it's equal to 1, that means this is the cumulative distribution function. But for us, this is just the probability mass function. We just use 0. So this indicates X equal to 5. If you use 1 here, cumulative, that's probability X less than equal to 5. Makes sense? Okay, next we move on to a very important practice. See, we didn't plot the distribution, right? So if we plot the probability distribution should be x equal to 1, 2, for this one 0, 1, 2, until 10, and what the probability looks like, right? So we will do this, use the simulation. So first we generate, so this is x1, that's a random variable. So followed by normal distribution, you trial total, you pick up 10 times, okay, trial 10 times, the success rate is 0.1. So we like to generate like simulate the process. You pick up once, and then what's the value? Keep picking up. How many times success? Okay. So the good thing is we can copy this. We just put here for reference. Okay. So this one, that's the one to generate a random variable followed by normal distribution. So this is the formula. Okay. Equal to, we can put here. C equal to, here you can generate any binomial, any variable, random variable followed by normal distribution. You just need to replace here this x1, n equal to 10, and the probability of success is 0.1. So what it gave us is just to show you your first trials, you got 1 success. Okay. So if we keep going, see, 2 out of 10 success. And the next time, like I tried 10 times, only 0 out of 10 success. And then like 2 out of 10. So this is to show you the x value, x1's value. It makes sense to you? So we can generate, so I would suggest this time you generate like 5,000 of them. It's like doing the experiment 5,000 times. So each time, that's 10 trials. This column shows value of x. Out of 10 trials could be 2 success, 0 success, 1 success. So the first one, so what's the expected value of x here? Or the mean? Anyone? Like in the long run, 5,000 times, what's the average you should be? It converts to the mean, 1. Yes, that's the NP, right? So equal to 1. So you will see, not surprised, you seldom see, oh, occasionally see a 4. Okay? Most of the time just 0, 1, 2, because it's around your expected value. So next we just to keep going. I want 5,000 times. So our plot will, it's more smooth. You just drag it down. What I do, I drag down to 1,000 and then copy, paste. That's much faster. Okay, so see, I have, this is 1,000. So I tried experiment 1,000 times. And then if you have PC, you just shift control down key, and then you copy this 1,000. It's like you copy the formula. And we want 5,000 times. So now I have 5,000 data points. So each point indicates 1 experiment and 1 value of x you observed. And also I can change this name as CX1. So this is, I generate the random data which follows the binomial distribution n equal to 10, p equal to 0.1. So next, I need to have it's not, you have both ways we want a sort of probability histogram. Okay? So normally, histogram for the continuous random variable, right? But here is a discrete one. So, but we still can use, you select all the data points and we just insert this histogram. Oops, I didn't select it. Select 5,000 data points. Just insert so this is something you don't want. You double click. So since I know this is the whole number, the value could be 0 or 1 or 2. So the width, I just use 1. The width of the bin, you use 1, just 1 unit. Okay. Oh yeah, this one is hard to see. I just use C. I just type in x1 follows binomial distribution, which is 10, 0.1. So you know what's the meaning here. So this is this bar shows this is the frequency. So we know we can either use relative frequency or density. So we also we change this to relative frequency. Okay, for x2, the easiest way, I would say I will make a copy. And then change name x2, and then I can change the data here. So here is x2. X2 follow the same or 30. X2 follow binomial distribution. The probability success is the same, but I pick up number of trials is 30 instead of 10. So we can click here, change the formula. Instead of we generate a different one, but n equal to 30. Right? If you use PC, you just double click, it's automatically copy paste the formula. And also this chart reflects the data. So the data changed, this chart changed, but this time is 30. Okay, so the shape changed. You look at x1, and then x2. So you also can do the same thing, copy paste the sheet and then change it to x3. You change the name. x3 this time follow binomial distribution, but that's 100 trials. Okay, and the success rate is still 0.1. Change this to 100 trials. So you look at the shape. So the first one is skewed to the right, very obvious. Okay, and gradually it's still skewed And then when n is quite large, okay, so this one, the shape is like a symmetric, like a bell shape. Copy. You look at this one, the first one, the x-axis up to 4,000, right? The maximum value here. And then this gradually changed. If we like to compare, we would rather this axis, right, have the same scale. Right? So if I change this one, double click. So minimum still to 4,000. We'll see what it looks like. It's like this, right? But that's what we want because we want them on the same scale. And then we copy paste on the first sheet, the first page. Okay. Yeah, for this, yeah, you can either just copy paste or you paste as an image. Both are fine. You can put here. And getting larger, you see. The shape gradually from the skew to the right, and then becomes like a symmetric. And also the center is here 100, that's 10 center around the expected value. So this is a very critical finding.